All right, welcome to the session on being lazy with Scala. My name is Venkat Subramaniam. We're going to talk pretty much about lazy evaluation and try to understand what that is and what are some of the benefits it offers and how we can make use of it. Best time to ask questions or make comment is when you have it. So if you have a question, don't hesitate. Please draw my attention and then ask the question. I'll try to repeat it, and then of course we'll try to answer your questions. So the very first question I want to start out with is, what does it mean to be lazy? Now, one of the things is we have been working with languages pretty much. Most languages we work with do what is called eager evaluation. And eager evaluation simply means as soon as you give an expression, it runs off and does it very quickly and immediately, if you will. Lazy evaluation is a way for us to postpone computations until we really absolutely have to execute it. And if we get really good at it, we can even postpone it to the point where we never have to execute it. Now, what is the benefit of doing this? The benefit of doing this is we don't often get efficient by running things faster. Sometimes we get efficient by eliminating things we otherwise don't have to execute. In a way, you can think about this like the law of running out, from a bear. It's not how fast you run that's important, as long as you can run faster than the guy behind you. So in a way, you basically eliminate computations, and by doing so, you get really efficient doing it. Now let's understand what this really means. Now, when it comes to programming languages, there are two different orders of evaluation. They're called applicative order and normal order. I'm not really a fan of this word called normal order because if it's so normal, you would see it so often. It's kind of abnormal order because we don't really see it. Most languages we program in use what's called applicative order. Now let's understand what that really means with a little example here. So if you look at an example of, let's say we define a function called add, and let's say add takes two values, let's say integer a and integer b, let's say. And then within this method, I'm going to simply say add over here so we can actually see it being called. And then I'm going to go ahead and say return a plus b. So that's my add function. Let's define a function called evaluate. And the evaluate function takes, let's say, an integer. We'll call it input. And I'm simply going to return the input given. That's all I'm doing. Now, of course, the last step here is I'm going to call evaluate. I'm going to call add over here and present, let's say, two values. Let's say 2 and 2. Now, a very simple example, as you can see, nothing really complicated at all. And I want to go ahead and run this little piece of code. And when I run this code, you can see it called add and returned a 4. But the question is this: when did it evaluate the add function? Everybody in this room knows the answer for it. It first evaluates the add function and then it calls the evaluate. That's called applicative order, like life is around us as we see it. But that doesn't have to be so. So let's look at one other example just to entertain this thought, if you will. Let's do this a little differently. I'm going to go ahead and write a function called add, which takes an a and b, and it's going to return an a plus b. This is a code written in Haskell just to get an understanding of what this means. I got an evaluate function which takes an input and returns the input again. And I'm going to do exactly what we did in Scala. I'm going to print evaluate and I'm going to call add with, let's say, 2 and 2. When I run this code, it produces exactly the same result as the Scala code did. But let's take a look at this a little differently. Now, if you notice in the Scala code, I put a print line statement and within the add function, and clearly I'm not doing that here in Haskell because Haskell is a language which is purely functional. You can't just go around and put print statements everywhere you want to. And so as a result, I cannot show this to you just like I did in the side of Scala. I got to apply a little bit of a different trick. I'm going to load this file called sample.hs, which is where the code is. I'm going to put a breakpoint on line number 1 and 15th character. Now that I put a breakpoint, I'm going to put a trace on this and call the main function. And it's waiting now at the breakpoint. Now I'm going to call, in this case, a history. And if you notice, I want you to pay close attention to this. This is, so to say, a sequence of calls it made. So read it bottom up instead of top down. So notice what you're seeing here. It started with main, and then it called evaluate first. And then after it called evaluate, it called the add as the very last step. This is called normal order. So in other words, what it did in the case of Haskell is, it first called evaluate. And you said, wait a minute, I'm passing a parameter with an add to you. It said, yeah, I noticed it, but I'm not going to run it. It's as lazy to the bone. It says, I'll get to it eventually. And then you called evaluate, and what did you within evaluate? Within evaluate, you said, I need the input, please. And so it said, oh, you want the input, I'll give it to you now, and that's when it evaluated. Am I making sense? So it postponed it until the very last responsible moment. Let's retry this, if you will, real quickly. I'm going to go back to this Scala code one more time, and notice in this case I'm returning a 42. Now what am I doing in this case? I am evaluating the function called evaluate, and I'm passing a parameter to it, which is the add function. But what am I doing within the evaluate function? I'm completely disregarding the input and returning an arbitrary 42. Which means any time and effort you spent evaluating the add is a total waste. Do you agree? Absolutely, right? So when I go ahead and run this code this time, notice how sad you spent all that effort running add and it never got used. Let's try this again in the case of Haskell. Now I go back to Haskell and do exactly the same thing. I'm returning a 42. But this time, let's go ahead and load this one more time. Let's set the breakpoint one more time. Let's call the trace one more time. And let's now call the history on this to see what it contains. And it says no breakpoints at all. So what does that tell you? It never actually ran the add function at all. It said, I'm lazy. Why bother wasting your time running it? So laziness, you don't say the word lazy so easily. You pronounce it a little differently. When you talk about programming, you say it's efficient. So laziness is really remarkable. And you saw how Haskell was able to do that very nicely without us having to do any work at all. Let's come back to Scala. After all, this talk is related to Scala. What can we do in Scala for this? Now, you know one thing already, isn't it? So notice in the case of Scala, well, let's talk about this. Some languages are born lazy. Other languages have to work really hard to be lazy. It's kind of like me, right? It's like taking a vacation is such a hard thing. My wife always laughs at me. Would you just sit down quietly? I'm like, how do you do that, right? So you have to really work really hard to be lazy. It's kind of like that. Well, Scala is born lazy. It intimidates me because you give it something to run, it says, I don't want to run this. Unless you really want the result, I'm going to postpone it. Well, Scala is relatively eager. Now, why is that? And the reason is very simple. Scala has a baggage it has to carry with it, which is it's got to run on the JVM. And JVM is not a purely functional environment. It is an environment where things are by default imperative in style. You cannot afford to be lazy when your functions potentially will have side effects. Now, think about languages that are purely functional like Haskell. You cannot write impure functions just so easily. If you want to write impure function, you have to write it with a special syntax, if you will. That's like staying in the. That's like the time you were in the elementary school. You got to get a token to go to the bathroom from the teacher, right? It's kind of like that. Can I be impure, please? Whereas in the JVM, we kind of default is impurity, and you put special effort to become pure. So Scala has to lean towards that way. But let's take a look at one other example here. Suppose I had a function here that says if, let's say, val, and let's say some variable input equals, let's say, 10, and I'm going to say if input is greater than 10, and let's say over here I'm going to call and add of 2 comma 3 is equal to, let's say, 5, then I'm going to print out, let's say, a result, whatever that means. Else I'm going to go ahead and print out no result. Now when I run this code, how beautiful that is. It only said no result. It never evaluated the add function. Now, of course, we all know this as short-circuiting, isn't it? However, what if I change this just a little bit? I'm going to take this add from here, and I'm going to put result equal to 5, and I'm going to say val result is equal to, and I'm going to just move it outside. Now, I didn't really change a whole lot semantically in this code, right? So instead of calling add within the if statement, if condition, I stored the result of add, and then I said use the result over here. But when I run this code, you would notice in this case, it did unfortunately call the add, even though you are never using the result. And again, we can see that Scala is actually very eager in evaluating that, and the short circuiting didn't really help us. If this was Haskell code, it would not even run the add because it says you never really used the result, so why should I care to really run it? But what can we do? How can we make Scala so lazy? Well, fortunately, we can, and notice this time, it's no longer running it. So I simply had to work a little hard to say, hey Scala, would you do me a favor? Treat result very lazily. If you never really use it, don't bother going around running it. So you are making the code lazy by really marking it with the lazy evaluation, and as a result, it's no longer evaluating it. So without the word lazy, you can see it does an eager evaluation of this particular function, but adding the word lazy, you can see that it's no longer evaluating it. So in other words, the variable is being postponed to be bound to this value until you first really use it in an expression. And if you never bind it, whatever function was going to produce the result for the binding never gets actually evaluated, and back we are to lazy evaluation. Of course, we got to be a bit careful when it comes to language like Scala to make sure that there are no impure functions in there and the correctness of the code is not being affected by it. But I showed you one example here, but in Scala mostly we get lazy evaluation because our function values are lambda expressions. That's where the real benefit really comes from in terms of how we can implement it using the lambdas. So to understand this, let's understand with a sequence generator, if you will. So I'm going to create a sequence generator. We'll call it as a print sequence. And the print sequence says start, I'm going to specify an integer. I'm going to say count, which is going to be an integer. But I'm going to specify here a generator, if you will, where the generator is a function that is going to take an integer and is going to return an integer. Now we all know that in Scala, this is called as a function value, right? So this is called a function value. It takes an input and returns an output. So how do I go about using this particular function value? So here's what I'm going to do. I'm going to simply say result is equal to, and I'm going to go to the generator and give it the start. Now I'm going to say for I is going to be value, let's say, from within 1 to the count, and I'm going to simply say print the result you have on your hand, and then result is equal to generator and regenerate a result for me. Now let's go ahead and try this little example. I call the print sequence. I'm going to start with the 1. I'm going to ask for 5 values, let's say 10 values, but I'm going to have to give a generator for him to use, and the generator is given an element or a number, just give me a number plus 1. Now if you notice in this case, what does this code really do? When I'm going to call the print sequence, this function here that you pass is not going to be evaluated at this time. It by default becomes a lazy evaluation. So in other words, in Scala, function values or lambdas are automatically lazy. They don't get evaluated right now. They wait until you actually call them until they get evaluated. So function values or lambdas are the gateway to laziness for a lot of stuff in Scala. So this is going to run this only when you call it. So within the function I'm saying, as many times as the number of count, please keep calling this function. So as a result, when I execute this code, you can, in this particular case, it would take the number and run it. So you can see in this case, it is counting those values. We could have obviously said plus 2, for example, rather than a plus 1, and that would be that function being evaluated. However, if I were to simply call this as, let's say, 1 to 0, you would notice that it never produced any result. Just to prove that point, let's go ahead and say 5 over here. You can see that's working. But let's go ahead and say in this case, I'm going to return the value number plus 2, but before that I'm going to print, let's say, called over here. So you can see that it's actually calling, but where does that calling actually happen? So I'm going to say in here, here at the start, and you can see that in this case, that only comes after the start, not before it, which tells us that this was evaluated very lazily. However, if I were to change this to a 0, you can see here at the start, and it says called because it called it once, but it did not call it any other times. So you can see that it's not going to come through at all, and that was because of this generator call, but not because of the calls coming in later on. So we can see we can start simulating the lazy evaluation very nicely. But this quickly bleeds into how collections are being implemented in Scala. In Scala, collections are considered to be strict collections. Strict collection simply means whenever you ask it to evaluate a function, immediately it'll evaluate it. It's very eager, and you say do this and immediately it does that, right? That's what a strict collection is. However, we can also have what are called lazy collections. So let me give you an example of going from a strict collection to a lazy collection, if you will. So I'm going to create a list of people here. So you can see in this case I have tuples, and this tuple is called Joe, Paula, and Jim, and so on, some names. And you can also see that there are ages of these people I have listed over here. Now I have a function called is older than 30, and this simply prints a little note and tells us whether the age is greater than 30. Now I have another function called name is 4 letters long, and this again prints a little note and gives us a result saying whether the name is 4 letters long. But let's go ahead and try using this, if you will. Now what am I interested in finding? Let's say I'm interested in finding the first person who is older than 30 years old but has got 4 letters in their name. What would that be? Well, in this particular example, Joe doesn't meet the cut, Paula doesn't, Jim doesn't. Well, Jane is the first person. She's got 4 letters in her name and she's older than 30. But how would this normally work if we do it using a strict collection? So notice what I'm going to do. I'm going to say print line. I'm going to take people on my hand. I'm going to filter from there. And I'm going to say is older than 30. Then filter again. And I'm going to say name is less than, is equal to 4 letters long. And I'm going to ask for the head. Now when I run this code, unfortunately, notice even though I got Jane 42 in the end, it did a hell of a lot of work. And that is the problem being eager, right? Remember how our parents always told, finish up your work right away? Well, they were wrong. Because the most cool kids are the kids who postpone things in the last minute, and they say, look, it's a snow day, I didn't have to do that stupid homework, right? They always were better kids than me. Well, that's what this code is doing. Runs off and does all the work right away. Let's see what really happened. We said people filter this is older than 30. It takes literally this collection and says, go ahead and check if it's 30, 30, 30, 30, 30, 30, and it did for all the elements. And that filtered out, Joe was removed, Paula was removed, Jim was removed, it kept Jane, it kept this other Joe, it kept this Bill, and it kept this Jill. Now we have about 4 or 5 elements left. Then it starts applying the is name letter 4 on each of the elements that are left. So as a result, it checks it on Jane, of course. It checks it also on Joe, and Joe gets rejected at this point, so Jane stays. And then of course Bill makes the cut, and this Jill makes the cut, and then finally we have 3 candidates, and then it picks the first one. But look at how extra work it did, and look at the number of output it gave us, and that's a lot of extra work we had to do. So look at the noise in this case. It's already clear that it did a lot of work. But we're going to change this into a lazy collection by using a view on this. So I just went to the people and I said people.view, that's all I did. So all I did was, a minute ago, I just ran this on people. It gave that lengthy output. I'm just adding a view this time, and notice a lot shorter output. And the reason for this now is it is extremely lazy. So it says, I don't have to run off and do all this work right now. I'm going to wait until I see all the things you want me to do. And once you told me all the stuff you need to do, I will do minimally what needs to be done. So in other words, you go to this people view and say, hey, go ahead and filter. It says I'm done, but it lies to you. And then you say filter, and then it says I'm done. Again, it lies to you. And then you say head. It says, oh dear, I better get my work done now. And it does only the minimum work to get that result, the head, and it's done. So you can see what's happening in this case. Rather than trying to go through a sequence after sequence after sequence, instead it simply took the first element and went through, and only if that was not satisfactory did it start with the second element. But at any time when it processed one element, if it reached the end it was satisfactory, it says I don't need to do any more work, I'm done. So the laziness really is directly benefit that you derive from it is the efficiency you get out of this. And you don't have to change the code structure. As you can see, the structure of the code was exactly the same as before, except that we turned into a laziness. So this is attained by using the people.view, and that gives you the laziness for this evaluation. But we can do a little bit different as well. In this case, we took a strict collection rather, and then we made it lazy. And so what's the difference in this case? Well, a strict collection is eager. It does things instantaneously when you call the functions on it. A lazy view on it says, I'll postpone it until I can no longer postpone it, and then only evaluate minimally to get the result. And any computations I did not have to perform, I saved big on those computations. So this is a big deal when it comes to reactive programming, because in reactive programming, you don't scale by doing a lot of stuff faster. You scale by doing only things you absolutely have to do and quietly remove things you don't otherwise have to do. And that is one of the biggest things. Reactive programming emphasizes on responsiveness, and you get responsiveness and scale by really being lazy at that point. That's one of the biggest benefits you get out of it. Well, that's great. But what if I don't have a strict collection? Can I still use some of these things? I'm going to define a function called isPrime, where I'm going to give a number to this isPrime. And what does this do? It simply says return number is greater than 1 and on a range of 2 to, let's say, number minus 1, it says exists, and it's going to ask if there is a value I where the number mod I is equal to 0, and I'm going to put a little exclamation around it to say it doesn't exist. Just as an example, let's say isPrime of 1, it is going to tell us in this case that there is no prime actually, that is 1 is not a prime, because by definition 1 is not a prime. What about 2? 2 is good. 3 is good. Let's try a 4 real quickly. 4 is not, and 5 of course is going to be a prime value, so that part is working. But I want all the prime numbers starting with a certain number. So I'm going to say print line primes, let's say from, and I'm going to ask you all the primes from value 1. So define primes from, and I'm going to say in this case starting, and I'm going to provide an integer, and I'm going to provide a list of the values, if you will. And what should I do here? I'm going to say if isPrime, the number which is starting, if that is true and if it is not true. Well, if it is true, I'm going to return starting, and I'm going to concatenate that with primes starting from starting plus 1. Otherwise, I'll simply return primes from starting plus 1. So if you look at this code, what are we doing in this particular code? I see a few people already laughing. Okay, that's fine, just stay calm. So the point really is what you're doing here is you're saying, if I have a number given to me, if this is a prime number, I'll give you that number followed by all the numbers that follow it. If not, I'll just keep that number and return all the numbers that follow it that are prime. Of course, I'm going to brave and go ahead and run this code, and what's going to happen when I run this code? It's going to run for quite a while, and eventually it's going to give you what? A stack overflow exception. It's still working. It depends on how much memory you have, right? So eventually it's going to give you a stack overflow exception. There you go. And why did it fail? Obviously because we are just recursing and recursing and recursing, and there's only so much you can do, right? So at this point you're probably thinking, all right, officially the speaker has gone mad. How do we get him out of the hall here, right? Well, but what if you're able to write code like this? Wouldn't that be so cool and expressive? Well, that is exactly what a stream is. So notice the change I'm going to make in this code. I take the list and I turn it into a stream. That's the first change I made. And then I go back and put a little notation to say that concatenate it. Now I run it. And notice it did not have a Stack Overflow exception. Instead, it simply gave me a stream with a to and, you know what, I'll get back to you on that. So that question simply says, oh, I'm lazy, I'll get back to it later. Now this is an infinite collection. What does it mean, infinite collection? Stream is an infinite collection which is going to have every single prime that you can imagine starting from 1. Hey, wait a minute, if it's infinite, where in the world would you store it? Now you know what all this cloud is about, right? Just kidding. So the point is, it is not what you're going to ask right now. If you never ask for it, it never generates it. So an infinite stream is a very clever and cunning stream. It says, I'm infinite, but I dare you to ask for the details. So obviously you won't call infinite unless you can store infinite, so you never ask for it. Somebody the other day asked me, what if I just call this over and over and over and go infinitely? Sure, go ahead, and you better be willing to face the consequence of running out of space eventually, right? So the point is, it's very infinite in size. But I want a range of values after all, so what do I want? I'm going to say dot take, and I'm going to say give me only 10 values. And guess what happens? It says sure, and what did it do? Absolutely nothing. Because that's lazy also, right? And you're like, okay, if all you bunch of guys are lazy and sitting down and doing nothing, how do we ever get a result out of it? Well, one way to get a result out of it is to say dot force. So this is like my house, right? My wife says, do this, my children don't. She says, do it, and they still don't. And she says, do it, or I'm calling daddy. I'm like, done, right? So the force is simply saying, you better get this done now, don't be any more lazy. So now you're forcing an execution on it. So at this point, you can see that it's going to go ahead and evaluate it and get you the result. That's one way to do. Or you can also call toList on it, and that's going to convert it to a list and give you the result. So you can do it this way. Or what you can do is you can say, well, give me values from 100, and you can see that it's giving you only the values from 100, and you can then of course put a list on it too if you want to, and you can see in this case it gives you those values, 10 values from 100, the prime values in a list. So the question then is, what's the difference? What's the difference between a stream and a lazy view? Because they seem to both be lazy. Well, the lazy view is lazy in evaluating the methods. The stream is ultimately lazy. It's lazy in even having the values in the collection. So a stream really has no values, and it generates the values only when you ask for it, whereas a view is going to be only lazy in evaluating the values. It's possible the values are already there, but evaluating the function may be postponed to a later time, and that is one of the things it provides for us. So we looked at an example of how we could go about doing this. So we looked at a lazy stream, and we talked about the difference between a lazy view and a lazy view versus a stream as well. But then, okay, we see these concepts, we can apply these into collections very nicely, that's great. But then the question is, how do we benefit from all of these? Now, this is one of the most fascinating things in my opinion is, once you get an idea about infinite streams and lazy evaluation, that is new to tools that you have on your hand, and now it's a question of trying to formulate your problems into an evaluation of lazy streams and lazy infinite collections. So one example that comes to mind for me is about tail call optimization. So let's talk about that real quick with an example. Let's say we are interested in defining a factorial, and in this case I'm going to say, let's say a number given to us, an integer, and I'm going to say in this case is equal to, and I'm going to simply call if number is equal to 1, return the number, else return, let's say the number times factorial of number minus 1. So I'm going to go ahead and call the factorial, let's say with the value of 5, and what is it going to do in this case? Well, in this case you can see that it's returning a 120, so it's pretty happy doing this. And I'm sure everybody has fascination for recursions, isn't it? Remember the time you found about recursion? I'm sure you celebrated that day, right? What a great idea. You could solve a problem using sub-problems. Isn't that amazing? I went out and played in the rain that day. I said, this is awesome. That's a way to do stuff. And I'm sure once you start using recursion, you got friends more so hanging out with you, right? Because you're the coolest person who can solve problems using recursion. But you know what happens eventually? There's always this one person that is not really thrilled about what you do, and that person comes to you and says, so you think recursions are cool, huh? And then they ask you to run that. What's going to happen now? Well, it's going to blow up with a Stack Overflow exception, isn't it? Well, that didn't go very well. The party is over, everybody leaves, and you're sitting there and saying, isn't that cool if I could actually use recursion? Which is really insane, because recursion is so cool, but you can't use it when you really need it, right? So wouldn't it be nice to actually be able to apply recursion? Well, the problem in this code really is the computation we perform here. If you look at the highlighted code, the last operation we perform here is one of multiply. So you are holding on to the number on your hand, and then you are saying, now go compute factorial, and when you are done, come back, I got more work to do. And so you start climbing the stack and then eventually hit the roof and this explodes. But what if the last operation is really the call to the function itself? So what we could do potentially is, we could now change it to fact, which is a big int, if you will, and then take another parameter which is number. We'll change this to a big int as well, and now we are going to say, if the number is 1, return the factorial. Otherwise, and the last call is factorial I want to call, and you say number times factorial, so you are performing the partial computation and pushing it on the parameter list, and you can step out of this function. So now you can go back and call this function by saying 1, 5, and now if you try to load this with a bigger number, you can see that it's no longer failing. It actually gives you a result. You can ask your other colleague to go memorize this result now, right? So the point really is, we don't have a Stack Overflow exception, but what did we just have? We had a tail call optimization. So the compiler smartly says, aha, you are calling the same function from the function itself, but only at the tail call position. So it quietly reworks the recursion into a simple while loop. So it turns a recursion into an iteration under the hood, and as a result, you can very nicely exploit recursion. Doesn't matter how deep your nesting would be, level would be in a regular recursion, you can try with a bigger input value also, so you get the full benefits of recursion. Now, JVM doesn't support recursion, unfortunately doesn't support tail call optimization or recursion. Let me clarify what I said. So JVM doesn't support tail call optimization recursion, but Java does, as we can, Scala does, as we can see here. However, what if we are not doing a simple recursion, a tail recursion like this? What if, on the other hand, we have a function where we don't call the function from itself, but let's say we are doing something a little different. We have a producer, let's say, which takes a number as a parameter, and this says if number is equal to 1, I'm going to simply return that value, else I'm going to call consumer, let's say consumer, and it then passes, let's say, in this case, a number plus 1. Now I define a consumer where I say, in this particular case, actually this is number minus 1, let's say. And then of course in the consumer I'm going to say, given a number, simply turn around and call the producer with the number itself. So this is a silly example, but nevertheless it shows what the problem here is. I call the producer with the 1, and you can see in this particular case, I'm just going to fire up this call and ask it to execute it. So in this case, I'm going to say this returns an integer. Let's go ahead and say this is an integer. And I'm going to say this is going to return an integer as well. So we are defining the type of these functions. What if I said a 2 and not a problem? What if I said a 10, not a problem? But what if I said a 10,000, for example? Well, that's not a problem. Okay, let's try a 50,000. And you can see that eventually it's going to blow up the stack. Well, what's the reason? The reason is, well, we were able to identify tail recursion very easily But when Scala is compiling this code, when it looks at each of the functions, it's quite possible these two functions are in two different files. It's possible these two functions are in two separate classes. It's possible they are compiled separately and then brought together. So Scala often doesn't have the visibility of stepping into another function to know what that function is doing. So even though this is recursion, we don't really see the tail call optimization kicking in. And of course, when we don't do these things, we often don't call it tail recursion. We can call different names, and in our field, we call it trampoline operations, because you're kind of jumping back and forth, but it's not as fun as trampoline, really. So the point really is that you are really jumping across these two functions back and forth, and eventually it fails. But wouldn't it be nice if we can apply this and get benefit out of this? Now you may wonder, what has this got to do with lazy evaluation? But if you want to really think about this a minute, think about a recursion as an infinite series of functions to evaluate. And the minute you think about this infinite series of functions to evaluate, what do you normally do at every single stage? You got a function on your hand, either you evaluate it if there's more to do, or you're done if that is the result. So in other words, you can quickly turn this into a lazy computation to say, keep calling it until there's no more work to do. And so it becomes a lazy infinite series problem if you want to think about it that way. Well, thankfully, we don't have to do much work for that. It's already done for us. So I'm going to go ahead and import right here. So I'm going to say import, and I'm going to bring in this import. I'm going to change this to a tail rec over here rather than just an integer. And likewise, I'm going to go ahead and change this to just returning the producer, and that's all I'm going to return. But then I'm going to change this to a done on a 1, and I'm going to change this to a tail call on the consumer. So now when I go and run this, notice it didn't fail, but instead it gives us a call object. What in the world is that? It simply says, I am going to be absolutely lazy. So when you go and call the producer is laid back and lazy. It says, I'm not going to do any real work for you. I'm going to just give you this call object and say, I'm done. So this is absolutely lazy evaluation, isn't it? And so how do I get the result out of it? Remember, we called the force method to do the work. Much like that, you're going to come down here and call a method, for example, called result. And you can see when you call the result is when it produces a result, not otherwise. So you can start going very large number of values, and you can see it's evaluating. But let's understand what this really means. I'm going to go back to 1 for a minute and run this, and notice the object you got back on hand. It is a done object you got back. So what is a done object? A done object simply says, I've got a result with me, I have no computations to do, and if you ever call me, I'll give you this result, right? That's all it says. On the other hand, if you don't call it with the 1, but if you call it with the 2, notice you get a call object and not a done. What is a call object? A call object says, I'm also a tail rec object, so they both are inheriting from tail rec. While the done says, I'm the terminal object, I have no more work to do. The tail rec object, the call object says, well, I am going to sit here, and when you call me, I will invoke the function I carry with me and simply get you back the result of that function and be done with it. And that result of the function in turn may either be a done or another call, and you got to go back and call that one more time. And if you never call it, you don't really progress any further. So it's extremely lazy until you on demand keep evaluating it until you get to the very end. So you can imagine what the result is going to do when I call result on it. The result is the one that simply sits there and loops through and says, keep calling, keep calling, keep calling until you get a done. And the minute you get a done, celebrate, you got the result. Otherwise, keep going. So it turns a recursion into a while loop, and as a result, it would never run into a Stack Overflow exception. But essentially, even though it's a very different set of objects and techniques, what are we really doing here under the hood? And what we are doing really under the hood is lazy evaluation, isn't it? So if you ask for the type of the class, just to get a feel for it, if I say get class, notice the tail call caller done, which is an inner class which implements the tail rec. On the other hand, if I change it to a to and ask for what the get class is, notice the call object, but both of those inherit from the tail rec, and as a result you can keep going. And so the result eventually turns into a while loop, like I said, and that's why when you say dot result, it is repeatedly evaluating the value over and over and getting the result for you eventually. So that is what we saw in this particular case, and we saw how lazy evaluation is used here for a completely different problem, which is implementing tail call optimization. But the minute you get a hang of this, now you sit back and say, I got an algorithm on my hand, but how can I conceptualize this algorithm so I can turn this into an infinite series problem and or a lazy evaluation? And the minute you do this, you're going to be so excited the first time you do this, like I did, because it's something you don't think about. And the reason is a lot of times the languages we work with haven't given these kind of set of tools for us. But the minute you realize that you have this tool for us in languages like Scala, it is like finding a new vehicle to go around, and that gives you the mobility and the agility that you never had before, and you start solving problems very differently. The result is the code becomes a lot more concise, the code becomes a lot more expressive, and as a result you're able to solve problems a lot more elegantly, and that becomes really fun. So this is something that I took time to learn because I grew up in the world of imperative programming. I grew up in the world of object-oriented programming. That's what I did mostly in my youth. As you can see, I had a very troubled childhood, as you can see, right? I wrote code in imperative style. I wrote code in object style. I was always dirty, and my parents looked, why are you like this? Until one day I learned about functional programming, and that didn't still make any sense to me. It's like, what in the world does functional programming mean? And I've been really trying hard to understand what that means. And the very first thing people told me is, it's all about immutability, and that only made things worse because I live in this world called slum where everything is mutable, right? And there's things pouring everywhere. And then you're saying, this is where everything is immutable, and to me that's like Narnia, right? Where everything is so beautiful, but I never know where the closet door is to walk through and go to Narnia. And that didn't make any sense to me. Why would I want immutability? And then I started looking around and I said, oh look, you could do function composition, and you could start putting these functions in nice little sequence, and you go function and function and function and function. And then that looked like a train wreck. Why would I want to do that? Why would I want to call all these functions in sequence? And then eventually I landed with lazy evaluation, and that was like finding the real answer for me. And that was like, wow, this is something that is really cool. So much that I want to kind of leave this thought with you as a final thought. To me, lazy evaluation is to functional programming as polymorphism is to object-oriented programming. I think it's the kick-ass feature of the paradigm. So it doesn't matter all the other stuff we talk about. To me, the really most fun part in functional programming is the lazy evaluation. That, I think, is what gives us the real benefit and essence. And once you really crack that nut and see how you can actually make use of it, that gives you the agility and the power. And if somebody comes to you and says, do object-oriented programming, but don't do polymorphism, you would laugh at them today, because the essence of object-oriented programming is polymorphism. In the same note, remember that first day you learned about polymorphism? I'm sure you were excited about it. But today, when you go to work, do you go to work excited saying, oh my gosh, I'm going to use polymorphism, right? You don't. You just kind of use it without thinking about it. And that's the kind of transition I'm going through, is I'm excited about lazy evaluation. I'm singing its song and I'm happy about it. But very soon I'm hoping one day I'll quietly sit there and write the code and not think about lazy evaluation, because that just becomes a second nature in writing code. And to me, that is kind of the essence of functional programming, is to really exploit the laziness in evaluation, and as a result take that to the next level, which is to gain efficiency from there on. I hope you found that useful. Thank you. Do we have any questions? Please. Yes, sir.
Yeah, how does the just-in-time compiler interact with tail recs?
So the question is, how does the just-in-time compiler interact with tail rec? Well, unfortunately, Java does not support tail call optimization at this time. So as far as Java is concerned, when I say Java, pardon me, I'm talking about the Java as the ecosystem, not the language. So the Java bytecode, the JIT compiler doesn't understand tail call optimization. So all it can deal with is just calling functions and functions. In the case of Scala, pre-Java 8 Scala, it's really as good as calling an anonymous inner class. And just like you would call thread in Java and send runnable to it, it doesn't call the runnable right away. It calls it later on when you actually invoke the thread.start. It's exactly the same concept. So this is much like passing an anonymous inner class. In Java 8 period, this would eventually turn into a invoke dynamic call. So as a result, that call to invoke dynamic will be postponed until you actually make the call. So in both cases, Java is completely unaware of lazy evaluation, other than saying, I'm not going to evaluate this function until you call it. And tail call optimization, if and when Java brings that about, I'm hearing that that's going to come in Java 27, but when they do, right, then we can benefit from that certainly. But until then, it'll be just a postponing evaluation to really saying, I don't have to evaluate this function until it's being called.
So you want to do non-trivial work inside each one?
Well, you want to do non-trivial work or not, actually it doesn't matter. And the reason it doesn't matter is as long as the work is pure, you can do anything you want to do in it. If it's not pure is when it messes with our brain because we're not sure when it's exactly going to call it. But it doesn't have to be non-trivial. Some of the problems you can solve with this can be pretty complex actually. And in a regular algorithm which is recursive, you will perform complex operations in each stage, but it doesn't care really. But at the end of the day, these are all just functions and you're only postponing calling to that function, that's all. So that shouldn't cause any problems per se. Please.
You know, some of us would say that the interesting feature is non-predicative Hindley-Milner-let polymorphism, which you find in ML as well. But lazy is really amazing because it lets you truly, between the two of them, you get to look at things in a very mathematical style.
Right,
but,
right. You're absolutely right.
The tail recursion stuff, which of course is built in Scheme, reminds me very much, I mean, you're getting very close to the real underlying thing, which is continuation passing style and call CC.
Yeah.
Is that something that you think that's coming down, or how do you see this as sort of like halfway to that?
So even in Scheme and with that Scheme, if you really stare at it for a minute, I would argue that's still laziness that's shining through it, right? So to a great extent, you're really employing laziness with other things. Continuations wouldn't be possible if we really were not lazy. So that's why I think laziness still rules at the end of the day. But for something as beautiful as that to be possible, I really think that the JIT compiler would have to support this. I don't think languages can do a whole lot dancing around this without real inherent support. The ideal day would be when you throw a recursion and you don't have to do anything and the JIT just swallows it, much like how invoked virtual happens today and optimization happens. That would be really awesome. I'm hoping Java would actually raise up to supporting that, even though I made fun of it. I hope it's sooner than that time period. That would be really nice, I think. Please.
So it seems like lazy evaluation is really useful in terms of recursion and stuff like that. How does lazy evaluation compare to using futures or promises, and when would you use one or the other?
So in a way, you could even argue that future and promises are also a bit of a laziness baked in, even though we are not really doing it as elegantly. So these are all different tools, and much like you're using polymorphism in OO, but you're using it for very many different types of patterns. In the same way, I think once we get a hang of laziness, the tail call optimization is just my effort to give one example of where this is a laziness, but I'm sure we can come up with 100 examples of that, and you just did, for example, right? So I think these are all, if I really look at it, it's like, oh look, I'm postponing this evaluation, and then as a result I'm furthering it. Whether promises or future are really nice composable thing, I would argue that that's where reactive programming has come up with a slightly different set of tools to work with. But again, that laziness kind of manifests itself, but I'm sure we'll find several uses of laziness in those cases and many more, I think. Absolutely. Well, I guess that's all we have. Thank you very much. Appreciate it.